These are the parts that make up the Vegas knob. There's this one. That's an internal part, which has the crown on it. This is what I call the body. These are both solid pieces of titanium. They required many different machining steps. The precision on both of these parts in certain places is under a thou. What I thought I'd do is I'd draw. So if we take a look at this and imagine it from this direction, sectioned in half so that you can see inside. A spot here for the O-ring, and then another O-ring back here at the back. Same on this side. So this is kind of like the outside of it. Okay, that's the knurling you see on the outside. Okay, so inside here are 3 bearing races. Here, another one here, and another one here, and corresponding race this side. Okay, goes across here. There's a center post, comes up about this high. I think it's about 80 thou in diameter. These bearing races are 1 millimeter for 1 millimeter balls. You can really see down inside there very well. So the diameter across here is 40 thou, 1 millimeter. Here's one of the balls. And here's one of the springs. Give you an idea how big they are. There's 4 springs and 4 balls. They fit inside the diameter, the holes that are in the diameter of this part. You can't see the hole there. The hole on the underneath side here slides onto the shaft, and this pin right here that's sticking up, again, this is a solid titanium piece, so that pin was machined on there in exactly the right location. That pin goes down through a hole here. And then there's the threaded shaft here with the blade. This blade is what interfaces with the switch. Now I flip this part over, you can kind of see those threads and that little blade right there. Not any different than the military knob, the ordinary knob that's been around for a long time. When we went to the 007, that was the first that we put threads on that shaft sticking down there and the blade. the 005s had a press fit kind of collar. Okay, so this is kind of what it looks like on the inside. Assembly requires a special fixture, and what it does is it enables me to put the springs in and the balls in after them and hold them in place, not unlike a fixture or a device that holds the rings on a piston as it's sliding into the cylinder. So I'm going to move these little teeny pieces out of the way again here. This over to the side. Now the crown piece, if I was to lay it on its side as well and section it and draw it here, it's going to look something like this. When it comes up, this is where the knurl is. And of course, it has a pin. It sticks down like this. And then inside here, it's got a shaft, the hole for the shaft. That. This is the knurl. Okay. So, how does it go together? Well, the holes that are around the diameter here, there are 4 of them. They hold the ball bearings, so when this is actually down here in place, this ball that's protruding out of this hole here, do them a little small on the scale, falls into this race. That's how the piece is retained. It cannot be pulled out because this part of the race comes around halfway around the ball, and when the ball is sitting here like this, if you try to pull the crown out, the ball won't let it come out. The other 2 races that are down here, these parts don't come around so far as I drew them. They're really more shallow. And all of them, when you push on the crown, in all cases, the ball just rides up and over and into the next race, and again into the third. So I have names for all these. This first one is called lock. The bottom one is the lock. The next race up I call unlock. And the last one at the top is spin. And you've already seen how this device works, in that you push the crown all the way down into the locked position, and in that case this pin here is protruding through down into the inside area here. I'll just kind of ghost it there a little bit so you can see that's really where that pin would be. So that pin actually comes down and interfaces with a modified version of the stop boss that's on the that's on the bearing surface of the body. The assembly procedure then is to grease these parts, put the springs and balls in the holes in the fixture, it holds them together, and then it allows this piece to enter in here, and once it's let go of, the balls come out into this first spin race, then it can no longer be taken apart. I haven't been able to take a single one apart without just completely destroying it. So the length of this pin is such that when the balls are in the unlock here, the pin is then pulled up to where it's right at this level here. In other words, it's no longer protruding down, but it's still sticking in the hole in the body. When you pull it all the way up to the spin, then this pin is now no longer even in this hole at all. It's actually up here. And when it's up there, of course, you can turn the crown and locate it into the 7 different locations, the 7 different holes that are drilled down through there. Probably can't see it in here. And there's also a cam-shaped cutout in the bottom of this main piece, which stops this pin from being able to spin all the way around. So when you're turning the crown, you can't spin it 180 degrees or 360 degrees when it's in the spin location. You can only click it to 0 through position 6. It won't go beyond. The detents that you feel when you're turning the crown, they come from this bearing race. So this bearing race was machined. This distance right here, from here to here, is just over 100 thou. So a very, very small cutter was custom made that has a 1mm tip to it. And this cutter, carbide cutter, comes in here, enters in this way, and then it can come out and start machining the race. And of course it machines all the way around the race, and then the next one, and then the next one, and it makes multiple passes for each race, including multiple passes for the interface between the races, which is way more complicated than I'm going to go into here. But the other thing that it does is, if you're looking at this piece here from above, and you're looking down at that spin race, the spin race has bump outs in it all the way around. So in other words, when the tool was going around in there, then it got to this point, it just bumped it a little bit, bumped it here, and what it did is it made it so that it made it so that the balls had little detents to fall into as you were turning the crown. And that's how come you can feel this click, 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 click. Not unlike how the knob feels when it's turning the switch. Just a little, but very subtle. Little click, click, clicks. And those detents make it possible to use this thing, because if the balls fall into these detents, then the way the thing is designed is this pin is now perfectly aligned over top of one of the 7 holes in the main body piece. So they had to be, those detents had to be machined all relative to where all the holes and the cam was put in the bottom of this piece. There are no detents, of course, in the unlock and lock races, because the crown can't spin in those locations. So they're just ordinary races. The races are machined to a tolerance of 1 thou. I had, because when you have a, if you take a look at this area right here, blown up very large, what holds this whole thing together is this ball is sitting right here, and then this comes away here. So if the part of the crown which has a hole in it can set just like this, and don't forget there's a coiled spring sitting here. when you try to pull out on the crown piece, this edge of the hole hits right at halfway point of the tiny 1mm ball, and then the ball hits right on this corner, this edge here. So if you have this precision too far one way or the other, where the ball goes out too far, or if it goes out too far, then it won't be easy to come into the next race, the next bearing race down. If it's not out far enough, then when you pull here, the whole device would just come apart. So the tolerance had to be pretty tight to make this work. And our first prototypes did work fairly quick, because I knew all this as I was drawing it in my CAD. I had already modeled these moving parts and checked to see that the balls would be in the right location and that you wouldn't be able to get it apart. I mean, we literally tried to pull, you know, the first prototype apart with great force to see if we could, and we were not able to. We've not been able to get any of them apart, even though some of them we wanted to, because they were damaged. As we were machining this part, the main part, this cutter quite often would wear out. And I think we got about 16 parts typically out of one cutter. The cutter cost us around $100. So just this cutter, just this one teeny piece, contributed to the expense of making these parts in a fairly large way. Typically you don't see a cutter, you know, only lasting that long. But the problem was it had to go down in here, and it had to remove this metal, and it was doing so. When you machine titanium, you don't want your cutter to cut through metal very far, and unfortunately in this kind of a cut, it was having to cut through a lot of metal no matter what you did. Okay, I guess this kind of sums it up. I wanted everybody to see, you know, how does it work? What went into making these pieces? This piece here, the main, was first machined on a lathe this way. So the end that goes onto the body was all finished with the bearing race, the threads, the screwdriver blade, the outside of it, where there's ID boring for the O-rings. The lathe that we use actually has the ability to lock the spindle in orientation, and a broach came through and actually cut the little teeny squares that you see there. And that same process also came down and machined this face where the dice are then later machined. And that's where it ended. Then it would come out and then just sever the part. The next operation, all the other operations in fact were on the mill, where this part was being held this way, and the cutters would come down and remove all the metal in here, which of course is this metal in here, and then this cutter here would come down and do the race. A drill would come down and put all these holes in. Another tool would come in and make sure all the holes were exactly the right size. You know, the cutters would come back then and clean up. So when you're machining parts like this, it's so tiny, you can't do any post work on them. You can't do hand work on a part like this because the part is too tiny. So you have to make sure that when it comes off the machine, it really is done. You can't scrape it. It just can't go inside of it. It's too tiny. With a tool, with your eye, even under the microscope, it's just very hard to do. So when that process was complete, then it went on to a 4-axis machine, a 4-axis indexer. It was a full 4-axis machine, but it was at an angle. It was kind of held like this, and then a tiny 1/64th end mill came down and machined all of the little markings for the dice as the fourth axis was rotating this part around like that. And it's at that point that this part was done. The cost of the metal, that doesn't factor in. The cost of the tools, a lot of these tools, that little teeny 1/64th end mill was not inexpensive like the larger end mills are, and it was chewing through them as well. On this part, it was machined on the lathe with 2 ops on the lathe, and then the final op was on the mill, where the mill had to come in with an end mill and cut this pin at this offset from the center hole. And this had to be so precise that when we loaded these giant, this part being made in a mill that weighs several tons, and this little teeny part is fitting into a special fixture made to fit the jaws of a massive chuck, but you have to hold it just right, and you have to come down and check them periodically to make sure that they are perfect. Your zero is perfectly aligned, especially in the direction that the vise is crushing the part. Anyway, that was machined with an end mill here, and then finally a drill, and again another ream had to come down and go into this hole to make sure that the hole was perfectly sized, because this surface here that was reamed had to perfectly match this boss that sticks up here, so that the two could slide on each other with almost no friction. That's a bearing surface, and you would feel it if we didn't get that perfectly smooth. Then when you tried to pull the crown up and down, you would feel the friction between these two surfaces. Okay, well, who knows if anybody actually listened to this whole video, but thank you if you did, and have a great day. I forgot earlier, this is the MakerBot model, and it's so large you can see in to see those races in there. See the boss, the holes, so you can count the 3 races that are in there. This crown piece, it only has 2 holes around its diameter, but the actual part has 4 holes, and it doesn't show the little pin coming down. It just has a hole where a pin would be, but in the actual titanium part, this is a solid piece, including the pin, one solid piece of metal. And we thought about making it with a hole and sliding the pin in, but that's just something that could fail, and I didn't want to go that route. Here too, you can see in there that cam shape, which comes right around to here, from there all the way around the holes. So the pin hits that and stops. So that's the thing that keeps this, when it's in its spin position, from going 360 degrees around.